Dear student, I am Dr. Harel Thomas, Professor in Applied Geology, Dr. Harisingh Gour, Vishwavidyalaya, Sagar. Today, I will deliver my lecture on pressure temperature PT path. Hope it will be useful for you. Try to be regular in course. A pressure temperature PT path is defined as the sequence of pressure temperature points experienced by a metamorphic rocks during its evolution. The thermo-tectonic evolution of rock give you the idea about the travel history of rocks, especially to inquire as to how the rocks reached these PT condition and how they have arrived back to the surface. Metamorphic petrologists assume that tectonic processes operating at plate tectonic velocities disturb the thermal structure of the lithosphere because time scale for heating thermal relaxation is much larger than that for tectonic disturbance. Oxberg and Turcotte 1974 were give the thermal modeling to unravel tectonic and thermal evolution of metamorphic terrain, which was later expanded by England and Richardson in 1977 and fully developed by England and Thomson 1984. Their thermal modeling take into account only condition as the main heat transfer mechanism. Thus, thermal relaxation would give you rise to PT T path that would be characteristic of the thermal perturbation and exhumation history. The PT path may be a sensitive monitor for many parameters: temperature change, the local structure setting of a rock and rate of tectonic transport. Therefore, the determination of the PT history may provide considerable insight into tectonic processes. Theoretically, the path taken by various rocks are given by curved loops in PT space. See figure on the screen, figure 1, the shape of which has interesting geodynamic significance. All path begins and end at the origin of the PT diagrams. Because this point represent the conditions at the earth's surface, there are an essential varied number of paths for any depositional environment, but they are limited by the maximum depth of burial of the bottom beds in sequence. The point of maximum depth of any rocks reaches in its movement path is called P max. From here onward, the thickened crust is adjusted to thermal relaxation or heating, during which a series of progressive metamorphic reactions take place. Eventually, the rock reaches its maximum temperature T max, the curved shape of a PT path result from complex mathematics of thermal modeling, but is explained in terms of physical processes involved. On every PT path, there is only one point that reflects the PT at the time T of equilibration of the peak metamorphic mineral assemblies. At this time, the rock has already begun to return to the surface as a result of isostatic uplift and erosion of the overlying rocks. With continued rise upward, the temperature begins to fall and most reactions cease. The high temperature minerals assemblies arrives at the Earth's surface. This type of pressure temperature time path is clockwise and characteristic in plate tectonic processes. See figure 1 on a screen. A cross section in figure 2 on a screen show the different stage from deposition to burial to recrystallization to exhumation of a rock shoot in form of clockwise movement, pressure temperature path characteristic of plate tectonic evolution of orogenic belts. Contrary to this movement path, there are geological situations when the rocks show anti-clockwise path in which heating occurs first and then loading and exhumation. The sense of clockwise or anti-clockwise is understandable only when the orientation axis indicates axis of increasing pressure from the origin towards the top, but when the plot P and its equivalent depth in a PT diagram, the P axis is shown increasing downward so as to better see within the earth. The particular pressure temperature time path followed by rocks depend on many factors such as style of deformation, number of thrust, number of fold phases and magma intruded, erosion rates and duration of the orogenic periods. Some petrologists have found that certain rocks, especially granulite, show counterclockwise PT path, suggesting that there are first a heating events at relatively low pressure succeeded by pressure increase and ultimately by cooling, that is for example, Sengupta et al. 1990, Sharma et al. 1992, Dasgupta 1995 and Thomas 1995 and 2005. That is T maximum followed by P max. It is designated anti-clockwise PT path, which is contrary to the movement path shown by rocks involved in plate tectonic processes. The shape of the PT path is shown in figure 3 on a screen. The counterclockwise PT path requires magmatic heat input early in the evolution, which is attributed to the crustal thinning and decompressional melting at depth where basic magma underplates the overlying crustal rocks. Reasons for the late P increase are unclear, but they are related to secondary melting in the crust to form granitoid masses. Remember that in anti-clockwise path, T max precede P max, unlike the clockwise path. Beside clockwise and anti-clockwise pressure temperature time path, there are two more type of path. First, the isobaric cooling path, abbreviated IBC with no recognizable precursor path and where initial retrograde path have a small positive or negative delta P oblique delta T slope. This IBC path seems to be related to rift environment. Second is isothermal decompression ITB path, which is the result of adiabatic cooling of rock during their upward movement. The contrasting pressure temperature time path between metamorphic terrain are due to the variation in tectonic or geodynamics pattern. Scientists in metamorphic petrology are largely devoted to calibrating the effect of various plate tectonic factors on the pressure temperature time path in young metamorphic belts such as the Himalaya. There are several methods to deduce the pressure, temperature, time path. These are: first, numerical modeling; second, direct petrological observation such as overprinting assemblies; another is peak and post-peak pressure temperature estimates; next is your zoned poikiloblast garnet; fifth is your fluid inclusion chronology. First, numerical modeling. In numerical modeling, the pressure temperature time path have been modeled from the range of physical and thermal parameters. Till date, very few pressure temperature time path have been derived. There are a few drawbacks of numerical modeling. First, the assumptions are simple in the modeling and hence are valid for natural example. Second, there are a number of derivations such as heat convection by fluid phase, heat advection by magma emplacement, large heat transfer not considerable in numerical modeling, nor does the numerical modeling link lower crustal melting and metamorphic effect in the upper crust. Hence, we consider direct petrological observation for deriving a pressure temperature time path for a metamorphic rock. Second, direct petrological observation. The direct petrological observation are inferred from mineral paragenesis, textural criteria, zoning in mineral composition, and geothermobarometric data on the minerals occurring in the rock under investigation. Pressure temperature path are obtained from A. calibration of geothermobarometric models, and B. petrogenetic grid based on the textural relation and experimental result. This dual relation in conjunction with geochronological data makes pressure temperature time path a powerful tool to make tectonic settling during regional metamorphism, where clockwise and anti-clockwise or counterclockwise path are recorded. Pressure temperature path provide a crucial link between crustal dynamics and metamorphic processes. First, overprinting assemblages. Many metamorphic rocks contain assemblages of two or more recrystallization events. For example, a sillimanite biotite potash feldspar plagioclase quartz gneiss which contain relict of andesite porphyroblast. The relict andesite is begin corroded and mantled by sillimanite in contact with potash feldspar. See figure 4 on the screen. The sub-assemblages sillimanite potash feldspar require that metamorphic temperatures reaches at least 650 degrees centigrade at pressure more than that of the aluminum silicate tipple point, but the presence of relict andalusite indicates that pressure did not exceed 3.76 kilobar and temperature 501 degree centigrade by Holdway 1971. The path of this rock in PT space is shown by arrow which passes from andalusite field to sillimanite field at same pressure above the triple point. See figure 4 on the screen. The path of this rock in PT space is shown by arrow which passes from andalusite field to the sillimanite field at same pressure above the triple point. See figure on 4. The return path is shown clockwise because granitic veins indicating melt formation are found in the area. Second, peak and post-peak pressure temperature estimates. This involve garnet, biotite, thermometer and garnet sillimanite plagioclase quartz barometer as applied to biotite and plagioclase inclusion with adjacent composition. Along a single traverse, the lack of inclusion along a single traverse would require some modifications to the method. Plagioclase, biotite and garnet composition in the center and rim were used. Pyrope contained in garnet is higher at rim and gives pressure temperature as 700 degree centigrade 7 kilobar, whereas core composition of garnet gives 600 degree centigrade 4 kilobar by same pair. The pressure temperature data with textural evidence in that mats of random sillimanite occur in both matrix and as inclusion in garnet. The pressure temperature path is shown. See figure 5 on screen, which indicates an early event M1 of high temperature and low pressure, while M2 event is high temperature and high pressure. This indicates garnet growth with loading, during which pressure and temperature both increase. The tectonic environment is obviously a thrusting after M1 events. Third, zone poikiloblast garnet. A large garnet in metamorphic gneiss from Greenville province, Tuclo et al. 1990 is subjected to chemical analysis. The traverse across AA line 5 millimeter long is taken by EPMA and chemical zoning profile is shown graphically. See figure 6A on the screen. The composition profile is plotted against the distance AA. See figure 6B on the screen, in which values are 0 where inclusions are present. In increase of pyroxene and decrease in XFE from core to rim indicates garnet growth during prograde metamorphism, which involved sillimanite involving reaction. Evidence by sillimanite inclusion. Spessartine and pyrope are balanced and gracilorite and almandine are also mutually compensated. Decrease of pressure during mineral growth suggested erosion of the tectonic pile concurrently with metamorphism. Pressure temperature path based on the chemical data shows late prograde or early retrograde clockwise path See figure 6c on a screen. Spear and Silverstone 1983 devised a technique for calculating pressure temperature path for garnet zoning profile that account for all possible reactions that are operative in a given assemblage. Spear and Silverstone in 1983 presented a method where the chemical zoning preserved in zoned garnet and plagioclase could be used to enter metamorphic PT path. An illustrative case of pressure, temperature, time deformation history in the Eastern Alps. The region south of Ternate window is called the Austro-Alpine basement or European basement that was involved in deformation and metamorphism associated with continental collision during alpine. See figure 7 on the screen. Himalayan orogeny, the polymetamorphic schist of the Austro-Alpine have been studied for thermo-tectonic evolution by Schwartz in 1997. The garnet bearing schist have preserved minerals of pre-alpine orogeny. See figure 8 on the screen. These minerals have been identified from microstructural control along with composition of T by garnet biotite thermometer and P by garnet plagioclase kyanite quartz from garnet core and rim composition. The mica schist as a tectonic unit show multi-stage tectono-metamorphic event of pre-alpine, Harisinghian and alpine Mesozoic age. The Austro-Alpine basement schist have been thrusted by nappes that crustal thickening during alpine orogeny. Schwartz in 1990 recognized 3 garnets of distinctive composition. See figure 9 on the screen. Garnet 1 is amine rich enclosed by garnet 2 and is cut normal to rotational Y. Its curved inclusion define internal cystosity Si. P and T yielded 7 kilobar 400 degree centigrade. Garnet 2 is classed as syntectonic rotational during growth around Y is evident from helicitic trials. Its curves normal to rotational axis X. It encloses pressure shadow spirals of quartz, plagioclase and mica. This garnet is bordered by biotite 2. P and T values involving garnet 2 are 9.5 kilobar 500 degree centigrade. Garnet 3 is positioned in microlithons. Crystal are broken by D4 shearing. Muscovite orientation along S3 indicates that S3 is a granulation cleavage. Pressure temperature values are 12 kilobar 650 to 800 degree centigrade. The reduction pressure temperature bath with radiometric edges and deformation component is in fact a pressure temperature time deformation path and shown in figure 10 on the screen. The path A to M represent successive stages of the thermo-tectonic evolution and deformation history from garnet and stolite. The recorded history started after intrusion of Caledonian granitoids at 434 million years, which are occur as orthogneiss. A to D is prograde path having deep burial of unit AAB beneath an overthrusted unit 2 of Pennine nappes. See figure 11A. D to E is isothermal decompression 4 kilobar when the thickened crust after overthrusting was isostatically uplifted. See figure 11B on the screen. E to H indicates increase of pressure temperature by further overthrusting of unit 3. See figure 10 on the screen. S to I is a retrograde path due to isostatic uplift and erosion. See figure 10 on the screen. Simple pressure temperature time path rather than pressure temperature path have been deduced by several workers from different areas. The Eastern Ghats belt of India is a gaolite migmatite terrain, and workers have shown a near complete ACW movement path. Sengupta et al. 1990, Dasgupta et al. 1995, Bose et al. 2000. Although counterclockwise path with isobaric cooling IBC is reported by Patel from Orissa sector of Eastern Ghat belts, Patel 2005. Again, anticlockwise ACW path from Sandmata Gaolites terrain Rajasthan is deduced from detailed petrological studies Sharma 1983, Sharma et al. 1992, Joshi et al. 1993, Thomas 1995 and 2005. A clockwise CW path is characteristically shown in orogenic belts including the Himalayan and Alps. Klotz et al. 2002 and 2005, and CW path may be explained by collision tectonics followed by uplift and collapse of thickened crust. Wendley et al. 1984. It is now recognized that CW and ACW path have complex retrograde trajectory. Harel 1989, Brown 1993, because prograde mineral assemblages, their composition and microstructure textures and structures are commonly modified or cease due to the lower temperature reaction and cations diffusion. Harel 1989, Brown 2002. A successful tectono-metamorphic evolutionary path must consider the time and pressure temperature values for different mineral assemblages and, if possible, the stages of pure and shear stress that the rock was subjected to during their evolution, rigid to the called pressure temperature time deformation path. Dear student, today in this lecture I have discussed about the pressure temperature PT path. In this topic I have covered the following heads: introduction, methods of determination of pressure temperature time path, numerical modeling, direct petrological observation, and an illustrative case of pressure, temperature, time deformation history. For further studies, please read the textbooks, references and the link given in the text. Thank you very much.